So exam 2 is going to cover sections 2.6 to 3.6 inclusive. 2.6 is shifting graphs, so we're going to start out by looking at some problems asking you to shift graphs. And the QR code that I have there, or the link here, will take you to this Desmos page. And we're going to start by figuring out what graphs these are. Now the first one here, call this example A. This is a graph of what kind of function? In general terms, what's the function that's being graphed here? What would you suggest?
Absolute value.
The absolute value, good. Now there's three things that have been done to this graph of the absolute value. As you can tell by this point here, it's been shifted to the left by 3, up by 4, and it's been flipped so that it opens down. So let's take care of those things kind of one at a time. Now as far as the horizontal shift is concerned, your horizontal shifts work kind of opposite of what you might think. So instead of instead of a minus for a shifting to the left by 3, you actually have to put a plus there. That causes your horizontal shift to the left by 3. The vertical shifts work in the direction that you think. Plus 4 is up 4, minus 4 is down 4. What's going to make this function open down as opposed to opening up? Usually it's a v that opens up. What's going to make it open down?
Negative in front.
Negative in front. Perfect. Thank you, sir. Let's move on to the next one. So I'll shut this graph off. Henry, question?
Could you just put the standard first and then how it's changed? Like
So
the first one is just the brackets and then the x.
Yeah, so what we're comparing this one to is the graph of the absolute value. Y equals the absolute value of x.
Okay.
All right. And now let me squeeze that in here for the next one. The next one, we'll see if you recognize it first, and then I'll write it down as well. So for the next one, shut that one off, turn this one on. If you had to take a guess, what function is it that gives us this graph before it gets shifted? Kind of looks like half of a parabola that opens sideways. Square root of x. Well done. Square root of x. Now our example of that has been shifted to the right by 4 and down by 2. You can see that by clicking on this graph and moving as far to the left as possible. So shifting to the right by 4, down by 2. I'll give you a second or two, or pause the video if you want to figure that out for yourself. So to the right by 4 would be square root of x minus 4. Remember, those horizontal shifts are opposite of what the sign tends to indicate. And then the last part was down by what, 2? So minus 2. Perfect. Let me just double check that. I want to make sure I got these in the right order. No, not that one. Oh, go away. Here we go. Yeah, minus 2. Perfect. So 2 down, 2 to go. So to the right by 4, down by 2. Let's do another one. So I'll shut this one off, turn this one on. This is a parabola that faces down. It's been shifted to the right by 3 and up by 4. So see if we can't do this one. What's the overall basic graph for the graph of a parabola?
X squared.
Y equals x squared. So it's this graph that's been shifted. A lot of times people forget the square there. I'm not sure why. They just put something in parentheses and forget that it's squared. I want to shift it to the right by 3, so what's going to go in the parentheses here?
Minus 3.
Minus 3, and then up by 4. There's one last thing that we need to account for here. The graph opens down, so what's going to make it open down?
Negative.
Yeah, a minus here. So minus. So let me make that a little bit darker, or maybe a little darker still. Minus. There we go. Let's use this to figure out the domain. So I'll go back to our graph. Domain is always going to be your x values. You can look at the domain in a couple of ways. One way you could say, well, I'm looking for places where the denominator is 0 or there's a negative under the square root or something like that. I want to throw those points out. I'm not finding any of those points for this one. So the domain is really just going to be negative infinity to infinity. You could also realize that if you recognize that this is a polynomial, and polynomials are defined everywhere. Now there's some fancy notation I like for negative infinity to infinity, and that's script R. I like that. That can be a bonus point for you if you remember that and use that in the right spot. I've gotten people though that put script R like on every single problem on the test, and they want extra credit on every single problem. Not going to happen. Just just be aware. You can do it though. Anyways, the range. We're going to have to think a little bit more on the range. Range is your y values. We want to go from lowest to highest. So the lowest y value that you're going to see would be what? That's going all the way down to negative infinity. Good, so negative infinity up to 4. And please don't give me x and y coordinates. I just want the y coordinates, lowest to highest. Is 4 going to get a bracket or parenthesis?
Yes. Bracket.
Bracket. So you're including the 4. So negative infinity to 4. Nice. Let's try some more here. So let's kind of scroll down in here. So we've got some graphs here. We're trying to find what are the equations of these graphs based on the graph of f. Now f is here in blue. Let's see if we can't figure out some of these other ones. Now for the first one, that graph's been shifted to the left by 3. So what would shift it to the left by 3? That's going to be a horizontal shift, so that would be f of x plus 3. So y equals f of x plus 3, that's your graph. How about the next one? That one got shifted up by 2. Now if it's a vertical shift, is that going to be something where I'm going to change the x inside the parenthesis or do something to the function outside the parenthesis? Well, vertical shifts are going to be taking place outside the parentheses. So y equals f of x plus 2. Let's move down to the third one here. Maybe it's easier to look at here. How did that one get shifted? How did graph 3 get shifted? To the right 2. So again, another horizontal shift. So it's been shifted to the right by 2. That means we need to make a change inside the parenthesis. And what's that change going to be? F of x minus 2. Excellent. Thank you. And the last one, this graph has been shifted down by 4. 1, 2, 3, 4. That's a vertical shift. Vertical shifts take place outside the parentheses. So this last one would be y equals f of x minus 4. Yay. While we're on the subject of graphs, a nice thing to be able to recognize is whether or not you have an even function. And even functions are easy to spot because they have a particular type of symmetry. And that symmetry is that they're symmetric with respect to, anyone want to fill in the blank? Symmetric with respect to, I'm being lazy here, with respect to the y-axis. Bonus points. Excellent. Excellent, excellent, excellent. All right, so let's move into section 2.7 then. A lot of what we did in 2.7 was working with functions and understanding some more about domain and range, and also working with some notation. So for instance, f plus g of 6. Now Desmos won't recognize that, but they would recognize f of 6 plus g of 6. And we're going to pretend that these are nice integer numbers, even though they're not quite. 2, 4, 6. F of 6, and I'm going to round that to about 2. G of 6, that looks pretty close to 5. So f plus g of 6, that's 7. Wow, you're done.
That was easy.
Yeah, I think that was a pretty good one. So hopefully you get a few dozen of those on the exam, right? Okay. These are a little more challenging. So f plus g, f minus g. Again, this is just function notation. If you were asked for f plus g of x, it's simply going to be square root of 36 minus x squared plus square root of x plus 3. The problem is, what's the domain? Again, the domain is the x values where these functions live. And this is where we're going to turn to that second QR code that I put on your handout, or the second link. Let's go to Desmos here. And let me turn on some graphs. So here's the first one, the top half of a circle of radius 6. Here's the second one. So the domain of the first one is negative 6 to 6. That's f of x. G of x, you can get the domain in a couple ways. It's not a bad idea to remind you, though, that what you're looking for as far as its domain is you want to make sure that x plus 3 is greater than or equal to 0, which means x is greater than or equal to negative 3. Cool. So that would be negative 3 to infinity in the interval notation. You can see that graphically right here. Starts at negative 3, goes out towards infinity. So nice. But now you want to try and find what's the domain of the sum of these two functions. And these two functions, when you add them together, are only going to be defined where they overlap. And they overlap starting here at negative 3, and then over here up to 6. So I should see this function graphed between negative 3 and 6. Let's see that that's the case. Bam. That's exactly what I see. Negative 3 to 6. Maybe it's easier to see if I get rid of these other two. Bam and bam. So the domain starts at negative 3 and goes to positive 6. So that would be the domain of f plus g of x. So its domain is negative 3 to 6. Domain negative 3 to 6. Beautiful.
And how did you add them together?
Oh, I just literally added them together. Now, what you could do graphically, if you weren't inclined to look at it on your graphing calculator or Desmos, is you could do it a different way. You could look at, well, where's f of x defined? And let me get out a sheet of paper here for myself. F of x is only defined between negative 6 and 6, right? And you can do that by figuring out where x squared, 36 minus x squared is greater than or equal to 0. But, so I got negative 6 to 6. That's where that function is defined. My other function was defined for x is greater than or equal to negative 3. So that's going to start here at negative 3 and mosey on out towards infinity. So here, all the way out to infinity. And their domain is where these two domains overlap. So they overlap right here, between negative 3 and 6. That's where they overlap. So if you wanted more of a graphical approach in terms of just looking at a number line, that would be it. Okay? So good question. Thank you. Okay. Let's move on down to f of negative 1. Some function composition stuff. So this is still some 2.7 work. Now they give you the function here. It's 2x minus 3. f of negative 1 really means this. Start out in the innermost parentheses, f of negative 1. If I put in negative 1 here for f, or into f, it's going to be 2 times negative 1, which is negative 2. Negative 2 minus 3 is negative 5. So what I get is this is equal to f of negative 5. Okay, we'll put negative 5 into this, to that expression, and end up with negative 10 minus 3 gives me negative 13. Done. That's all you're looking for there. And let me zoom out a little bit. There you go.
Can you re-explain the first step quickly?
So this is just the notation. That if you write it like this is function composition. It's the outside function, then the inside function. So for instance, your next example is this one down here. G composed with f of 2. That's one way you could write it. Now, a better way to visualize and understand that is this way here, is to think of that as G, the first function's on the outside, of f of 2. And the second function's on the inside. So it's just different notations as far as the way you want to write it. I like this one better because I think students relate to this a little bit easier. This is what you're going to see sometimes in WebAssign and maybe occasionally on a test, but not often. I tend to be a little bit more student friendly with the choice of problems I give, so I'd probably write it like that. So let's take a look at this one. Maybe it's written like this, G of f of 2, which you would then translate in your mind to G of f of 2. And again, you want to work from the inside out. Now in this one, they only give you a table. You're not going to be using decimals for this one. So let's start here. F of 2. Find 2 up here. There's your x value. What's f of 2 going to equal? Anyone? How about one of my homies? Want to shout out there? Your chance for 5 seconds of fame. What's f of 2? That would be 3. Thank you. So now I got to go to the function and figure out what g of 3 is. So here's your x value. X is 3. What's g of 3 going to equal? G of 3 would equal 2. And you're done. That's literally all there is to that one.
I'm still confused in the first one, so where did the negative 5 come from? The one above.
So f of negative 1 from the previous one is going to be 2 times negative 1 minus 3. So you're plugging in the negative 1 into the function for x.
Oh, and then use that solution and plug it in again?
Yeah.
Oh.
This is what's called an iteration. You're doing the same thing again and again. So like your graphing calculator is good at doing iterations if you set it up the right way. Let me see if I can't get it to do something. Close, clear. So when you take the old value and put it back in the function to a new value, that's called an iteration. So I could do, say, 0.9 squared. And then I could take my previous answer and square it. So second answer squared. And I can keep on squaring that value. So I squared 0.81, I get 0.65 something. If I square this, I should get something around 0.4 maybe, 0.43, and keep on squaring it. So each time I hit this button, it's going to take the output from the old function, put it into the new, put in the function again, and keep on going. So eventually it'll get down to 0, or very, very close to 0, as close as you want. Let's move on to section 2.8. Here's a nice one. It's a very friendly one. if 6, 9 is on the graph for the function of f, then what point is on the graph of the inverse? Remember that one? 9, 6. What do you think? Can you give it some love? Yeah. I think
That
so.
was easy.
Yeah, that should be a giveaway on an exam. Here's a slightly harder way to ask the same kind of question. So remember that the roles of x and y interchange when you go from a function to its inverse. So here's x, here's f of x. Those roles interchange over here. So x and f inverse of x. So what you're saying is that I want to put in negative 45 into my function f inverse and figure out what the y value is. Well, that x in my inverse function comes from the y in my function, right here. So the question is, well, what's the x value? Because if I know that, that's going to tell me my y value here. So all I have to do to find that is set f of x equal to negative 45 and solve. So I'm going to find the x value that gives me this y value, and that'll be my answer. Subtract 3 from both sides. Negative 48 equals negative 8x. Divide both sides by negative 8. What do I get for x? Six. So that's 6. Plugging in 6 here gives me negative 45 here. So f inverse of negative 45 gives me a 6. All right, not going to be hitting that easy button, but hopefully it's not too hard either. So comments or thoughts on that one? All right. Sticking with the inverse stuff here. And maybe it's easier to see if I pull it up on OneNote. So let me do that. Oh, you know, we skipped one somehow. How did we skip this? No, we did that one. Never mind.
You only did the first part of it, though, I think.
Yeah, you're right. You're right. Yeah, let me go back and. No, we did that one. Okay. All right. So let me just come down to here. So, does this graph represent a one-to-one function?
Yeah, passing the horizontal line test.
Beautiful. Complete answer, worthy of full credit on an exam. Yes, it passes the horizontal line test. Now, be advised, I'm not going to give you credit for just yes or no on an exam like, for a question like that. You need to tell me why. And the reason is it passes the horizontal line test. So it's a function, it passes the vertical line test, and it's a one-to-one function, it passes the horizontal line test. So now, the fact that it passes the horizontal line test is really, really cool. So yes, passes the HLT. Does this graph have an inverse, which is also a function? And it's kind of yes by the same reason. Yes, because it passes the horizontal line test. That's the nice thing about functions that pass the horizontal line test. They have an inverse, which is also a function. So the answer is kind of the same to both. If the point 4, 3 is on the graph of the function, what point is on the graph of the inverse? So if that point's on the graph of the function, what's on the graph of the inverse? 3, 4. So 3, 4. So there. In fact, if you reverse a couple of these, so this one is at 0, 5, so that means the point at 5, 0 is here. You can actually figure out what the graph of the inverse looks like by reversing just a few key of these and then playing connect the dots. Let's ask another inverse type question. F inverse of 2 Well, remember that 2 that you're using as an x value for the inverse came from the y value for the function. So the question is, what's the x value that has a y value of 2? So here's your y equals 2. What x value goes with y equals 2? 5. Come over here, strike the graph here, come down. You're at the x-axis at 5. So the answer here is 5. Two more problems with inverses. And let me show the first one here. Maybe I can make that a little bit bigger. Use the inverse function property to determine whether f and g are inverses of each other. Now let me remind you what the inverse function property says. Basically, it says that f of g of x is x and g of f of x is also x. If that's true, then f and g are inverses of each other. Now, there's a couple ways I could ask that question. I'm not really going to be anxious for you to plug in f of g of x and g of f of x and compute and get x, but I will show you one of those. Let's do f of g of x. So f of g of x really means, since g of x is x minus 4 over 8, or x minus 8 over 4, I'm going to replace g of x by that. And then I'm going to go to the rule for f. And the rule for f says, okay, take 4 times x plus 8. Except now, instead of an x, I'm going to use this expression here, x minus 8 over 4. And I get lots of nice simplification. What's the first thing you can see that'll simplify? Cancel out the 4's. That leaves me with x minus 8 plus 8. And the x's cancel and gives you x. If you did this in the opposite direction, you would again get x. And that's telling you the big conclusion here, which is that f and g are inverses of each other. That's the big thing to see here. Do you remember how the graph of f of x is going to look in comparison to the graph of g of x? I'll show you in the next one then. We'll actually calculate the inverse here.
On the exam, would we have to do both equations, f of g of x and g of f of x?
You know, that kind of grunt work is not my style of question, to make you do that both times. I mean, I could, but what I want you to know is that if this does happen, then the functions are inverses of each other. What I also want you to know is how to find the inverse of a function. So that would be by setting y, replacing f of x by y. That should be a cubed. Interchanging x and y, x equals 8 minus 4y cubed. Solve for y. So I'll move this to the other side and this to that side because I want to get the y by itself. 4y cubed equals 8 minus x. And then to finish solving, I'm going to divide by 4 and take the cube root. So, this is kind of still step 3 here. Y equals the cube root of 8 minus x over 4. Now there's probably one last thing that I would want from you in this type of problem. I shouldn't say probably, I do want it. I want you to write that as f inverse of x is equal to all that mess. So that would be kind of the finished product in that one. Let's take a look at it graphically. One thing you should know about this graphically is how they relate. Before I get there, Henry, yeah, go ahead.
So in step 2, you just switch X and Y? Like you just switch
Yeah, step 2, you're just switching X and Y. Wherever there's an X, you write a Y. Wherever there's a Y, you write an X. So yeah, it's exactly what's going on there.
For 4 instead of y, you just put f of negative 1x.
Yep, it's the inverse notation, f negative 1 of x. The one thing that I want to remind people is that it has nothing to do with the reciprocal. Some people try and give me f inverse by finding the reciprocal of this. If I graph the reciprocal, it wouldn't look anything like it's supposed to. Now, as far as the graphs are concerned, let's take a look here. Let me shut that one off. Here's the graph of the function. Here's the graph of the inverse. Let me just square these up. What you should see is that these are mirror images of each other around the line y equals x. So if I type in y equals x here, bam, they're mirror images. You'll also see similar points, like 0, 8. What would this point be then? 8 and 0. This point, kind of ugly, 1.26 and 0, but this one's going to be 0 and 1.26. So it has that mirror image about it that you would expect for the graph of a function and an inverse. That's, by the way, a good way you can tell whether or not you calculated things correctly, is do the graphs look okay? Make sure that if you're using Desmos, you click this. That way it kind of gives you a nice even look to things. Sometimes, you know, if your axes aren't equal, then even though you do things right, it might not look the way it's supposed to. So give that a good click and then move things around. All right. So much for inverses. Let's move on to quadratic functions. So these down here. Y equals negative x squared plus 6x minus 5. Now a couple things I could ask for here, and I'm probably going to go through this way too fast, but I want to get through this before time ends. One thing I could ask for is this to be written in standard form. That's y equals a times x minus h squared plus k. Doing that for this type of problem, or this one, is a little bit of a pain. The nice thing is that when you get it in that form, you can just look at this and read off the x and y coordinates of the vertex. It'd be h and k, that's your vertex. Vertex h comma k. But if you have to put it in that form from scratch and show your work, that's a lot of work. Let me show you. It's going to be y equals negative x squared plus 6x minus 5. I'm going to move the 5 to the other side for the moment. When it changes sides, it's going to change signs. And I have to complete the square. I can't complete the square unless I have a coefficient of 1. And I don't. I've got a coefficient of negative 1. So here's kind of an extra step for not only this one, but for the next one. You have to factor that out. So I'm going to factor out the negative. Don't factor out the GCF. Don't factor out a negative and an x. It just doesn't work. So I'm going to factor out the negative. If you distribute it, you get negative x squared plus 6. So these things match. Now the question is, what number do I put in there to complete the square? If you remember back to your intermediate algebra classes, what you're going to do is you're going to take half of this number. So half of negative 6 is negative 3. Negative 3 squared is 9. So I'm going to put a 9 up there. And it'd be wonderful to tell you that I'm going to put a 9 over here, but that's not quite true. What do I need to put on the left-hand side? Not 9,
Negative.
but negative 9, because there's a negative out in front of this. So in effect, I've subtracted 9 here. I've got to subtract 9 here. Thanks, William. The left-hand side becomes y minus 4. the right-hand side becomes negative of x minus 3 squared. And so finally, I want to move that 4 to the left-hand, or to the right-hand side. Let me kind of do things here. Y minus 4. If I move the 4 to the right-hand side, I get y equals negative x minus 3 squared minus 4. Wow, get the oxygen back, man.
I thought it was plus 4.
Plus 4, thank you. That's a lot. That's a lot of work. We're going to have to do a faster job of that in the next one. The max coordinate, if I'm looking for the y coordinate, don't give me the x and y coordinate. In fact, hopefully you can see the vertex here. What's the vertex? 3 and 4. Hopefully you can write that off. 3 comma 4. And the max, or min or max, depends if it's open up or down. This one opens down, so the max coordinate is just going to be a 4. For what values is this greater than 0? Let's actually look back at the graph here real quick. This graph's going to open down. It's going to be greater than 0 for the x's between 1 and 5. So 1 comma 5. That's where this graph's going to be greater than 0. Now, am I going to include the endpoints on that? The answer is no. I want to know where it's greater than 0, not greater than or equal to 0. All right. We did a lot of work here. I don't want to do as much work with this next one. So with this next one, I'm going to take advantage of the fact that I can graph these. I can graph it on my graphing calculator. I can graph it on Desmos, whatever I find convenient. But let's shut off that one and turn on this one. And right away, I can see that, oh, there's my vertex, 1, negative 5. Beautiful. So the thing is, if I want to put that in the nice standard form, that 3 out in front here, that's going to be my A. And then if I know H and K, then I'm in really good shape. Then I can just plug them in here. So let's look back. The vertex was at the point 1, negative 5, so that's my H and K. Let's write that down here. The vertex is at 1, negative 5. So that's going to allow me to put that in standard form. It's going to be y equals A, which is 3, x minus h squared plus k. Here's h, here's k. So I'll put in a 1 here and a negative 5 here. I'd probably clean it up like this. Y equals 3 times x minus 1 squared minus 5. And you're done. Beautiful. So that's your standard form. A lot friendlier than what we did with the last one. X and y intercepts. How do you find the y-intercept? Set x to 0. Now you've got two different forms of this equation that you could use. You could set x equal to 0 in this form right here, or you could set x equal to 0 in this form right here. But I argue that it's easier to do it over here. Because if you set x equal to 0 here, well, the first term is 0, second term is 0, you're just left with negative 2, right? So you get 0, negative 2, that's your intercept. X, y, 0, negative 2. For your x-intercepts, that's going to be a lot more work. Again, you've got two choices. You can use this one or this one. Let's take a look at what happens if you use this one. If you use this one, if you set this equal to 0, you probably end up using the quadratic formula. No big deal there. Quadratic formula is fine. But what if I set y equals 0 here and got 0, I should say, yeah, here, equals 3 times x minus 1 squared minus 5. What I would do is I'd move the 5 to the other side, then divide by 3, and then take the square root. Make sure you take plus or minus the square root. And finally, add 1. And there you go. There's your two roots. 1 plus or minus 5 times the square root, 5 over the square root of 5 over 3. Beautiful. So, I don't know. What are you inclined? Do you think you'd like to do the quadratic formula here or square root property here? I think that feels a little bit less painful. It's up to you. Okay. You can answer some domain and range questions. The range is going to go up to, or actually start at -5 and go up to infinity. The domain is going to be everything. You're not going to be given this on the exam. You should have this kind of more or less memorized. What happens with your even and odd functions with positive or negative leading coefficients? It's the end behavior. There's only 4 of them. So basically, if you have an odd degree with a positive leading coefficient, as x approaches infinity, y is going to approach infinity. That's what's going to happen to your y value. If x approaches negative infinity, y approaches negative infinity. So they both kind of go in sync. So moving down to this one, and this isn't really written wonderfully. I would say as x approaches infinity, y is going to approach infinity because it's that first type of behavior. As x approaches negative infinity, y also approaches negative infinity. You have to look at and key in on the degree and the leading coefficient. Is the degree positive, or is the degree even or odd? And is the leading coefficient positive or negative? In this case, everything lined up, so we're going to use the first of those 4 possible end behaviors. Let's figure out the end behavior for this next one. Pause the video if you like, see if you can figure out which end behavior it is, and answer as x approaches infinity, what happens to y? And as x approaches negative infinity, what happens to y? So, while you're thinking of that, I do believe I have a little bit of that stuff here. If you have a positive leading coefficient, then as x approaches infinity, y is going to approach infinity. Or negative infinity to negative infinity. That was our last case. When you have a negative leading coefficient and odd degree, those things are flipped. If you have an even degree and positive leading coefficients, both of these point up. Both are going to head towards positive infinity. But we don't have that. We've got something that looks like this right here. So eventually, the behavior here, the end behavior for both of these is that they're going towards negative infinity in both directions. As you move out towards positive infinity, as you move out towards negative infinity, both of them are going towards negative infinity. So eventually it looks like this. Not perfectly like that. I might have to zoom out considerably to see that, but oh, that's the wrong one. Here. There we go. Yeah, they are going towards negative infinity. Nice. All right. And behavior is not limited to just our polynomial functions. We can see it with our exponential functions. So that'd be something like this. Y equals 5 to the x minus 7. As you move out towards positive infinity, move out towards the positive direction, the y value is just going to get bigger and bigger and bigger. It's exploding. So coming back to our little handout, as x approaches infinity, y approaches infinity. That's not true as x approaches negative infinity. As x approaches negative infinity, let's see what happens to the graph. You can put a tracer on this, kind of drag, and take a look at the y coordinate. It's not going towards negative infinity, it's getting closer and closer to what number? Closer and closer to -7. This number right here, in fact. So, -7 there. Beautiful. Now, let's play around with some graphs. And these are going back to our shifting a little bit. The graph of -x⁴, I had that up just a second ago. Let me put that back up here. That's this one. But that's not what we have in this particular problem. So in this particular problem, we've got negative of x plus 2 to the 4th. Now, I'm very likely to give you this graph without any numbers. But we don't really need the numbers to understand that this cannot be the correct graph. Why not? Well, it's opening down. That much is correct. But what kind of a shift would the plus 2 cause? Shifted 2 to the left. But which way was this graph shifted compared to y equals -x to the 4th?
Either way.
It was shifted down.
Or
Shifted down. So you don't necessarily need the numbers on the scale here to realize that, oh, this can't be the right graph. It was shifted down. In a similar way, this one was shifted up. So neither of these could be the correct graph. Let's try another one kind of like that. Now, the big thing to see here is, well, there's a few of them. First of all, that's positive. -1 is going to cause a shift right by 1. How about the +1? How's that going to shift things? Up 1. Now, the graph of y equals x cubed, y equals x cubed. Let's go back to that one. That's going to look like this. So right away, both of these graphs have the wrong shape. They're shaped like this kind of graph, -x cubed. So neither of those could be right for that reason. But beyond that, looking at the graphs, this was shifted left and down, this was shifted right and down. So neither of these had the right shift. Okay, polynomial division. I know you guys love this one, which is why we're going to include an example here. 4x to the 4th plus or -2x cubed plus 20x squared divided by this. Woohoo! Wow, that's a lot, which is why I have it pre-done. I'm just going to talk about this a little bit. There was 4 steps: father, mother, sister, brother. Figure out, multiply, subtract, and bring down. Here's your figure step. You're going to take the leading coefficients, leading terms I should say, and divide them by each other. That gives you your 2x, which I put up here. These are color-coded if you're looking back at this later. Take the 2x and multiply by this whole term out in front, right there. When I distribute that, I get this. Subtract. What's my trick for subtraction? Does anyone remember? Change the sign and add. So that minus became a plus, that plus became a minus, etc. Add, that gives me a 2x cubed, but I also need to bring down this term and then repeat that process. Eventually you get a quotient plus a remainder over your divisor. That's how they want it written when it's all said and done. So there's a good example. Take a quick look at it or pause the video. Synthetic division, I hope you can do that one. I'm going to skip that. Rational root theorem. Oh boy. Rational root theorem. There's a couple numbers that are factors of 2, 1 and 2, and a couple numbers that are factors of 10, 1, 2, 5, and 10. Your possible rational roots are going to come from this. This is your Q, this is your P. You want to look at combinations of plus or minus P over Q. Now when you're doing this, just kind of be methodical. Do 1 over 1, and then 1 over 2. Actually 1/2. And then 2 over 1. And 2 over 2 is 1, so I don't need to list that twice. I'll start over. 5 over 1, and then 5 over 2. 10 over 1, and 10 over 2, well, that's 5. So I've already included that one. Those are your possible rational roots. Make sure you do the plus or minus for those. Any of your roots that are rational, that is fractions, have to come from that. So that's this one down here. Let me clean up the graph a little bit. And you can see them. Something looks wrong here. 2 squared. 2x to the 5th plus 6x cubed. Plus 2x squared minus 10. So we got one rational root there. That means the other two have to be complex, because I only see one place where this graph crosses the x-axis. All right. Boy, I started at what I thought was really enough, and it's still not enough time. Let me keep going. If you got to leave, hey, I understand. We are at that time. Let's see. Moving down to the next one. X to the 4th. No, I'm going to have to skip that one. Let's do this one. Okay, so moving on down to this one here. It says find all real zeros, use the quadratic formula if necessary. So what that's going to mean for us is I would suggest you start out by finding one of the roots, and we can see that from the graph up above. Right here you can see that there's a root at -1. So what you'll do is use synthetic division and say, okay, if -1 is a root, then by synthetic division, I get this. That turns my polynomial p of x into x plus 1 times all this. And as far as finding the rest of the roots are concerned, then you'd have to set this equal to 0 using the quadratic formula and solve. And so that would be it for that one. Likewise, you do something similar here. You factor out the x, use the quadratic formula on this one. If you were to actually look at the graph, there would only be one place where it crosses the x-axis. So that means the other two have to be imaginary roots. So something like that. If something has degree 3 and roots here and here, then it's x equal 3, x equal 5i. Now, if I give you a problem, I'd probably give you this much, because these roots have to occur in conjugate pairs. So the other one would be -5i. And then you'd find your polynomial by moving these things to the other side, and then multiply these together, x minus 3, x minus 5i, and x plus 5i. were to the y's, I would suggest you do the complex parts first. You'll end up with x minus 3 times x squared plus 25, and then that will be your final answer when you're all done with that one. You should expect some work on rational functions to kind of close things out. You should be able to find the intercepts. Generally speaking, finding the x-intercepts, you set the numerator equal to 0. To find the y-intercepts, set x equal to 0. The vertical asymptotes, how do you find those? Set the denominator equal to 0. You should be aware of end behavior as well. That can apply to our rational functions. Something like this would be a rational function. If I ask you for the vertical asymptotes, you'd give me something like this: x equals 5, x equals -2. I want equations, not just -2 and 5. So, for instance, this one would have vertical asymptotes at 4 and -1. And likewise, you can figure out some of the rest of these things as well. All right, I realize I'm out of time. Hopefully you find that helpful. That's, boy, that's 90% of what I could ask, period. Last minute comments or questions? I will post this on YouTube. So, see ya.